Welcome, geometry. Back to everyone's favorite time, I'm sure, of the day when you're watching me scribble a whole bunch of nonsense on the board. Unfortunately, with how things are going with the coronavirus, we won't meet again, and we're actually accelerating our timeline a little bit. So today we're going to do 2 sections in this lecture, because we actually miss out on the school day, technically, with missing out on Monday original. So 2 sections today. First one we're going to do is 13-4, compound probability. If you want to follow along, it's page 844. Eventually we got on to 13-5. Okay. So the first thing is, for compound probability, we know we need to talk about something called a compound event. A compound event, as one could imply, just means that 2 or more events occur. Now remember, when we talk about events, that's just something that happens. Like if I roll a 6-sided number cube, that's an event. Now, a compound event, I just need multiple things to happen. So let's say I roll a dice and then I flip a coin. That'd be 2 things, that'd be a compound event. So there's 2 types of compound events. We have independent where the events don't affect each other. Events do not affect each other. Again, based on that example, where if I roll a 6-sided number cube and I flip a coin, the coin does not affect my dice at all. My dice doesn't affect my coin at all, unless somehow they were to smash into each other and affect the result. But they would not have any influence over each other, so they'd be independent events. So, if that's what an independent event is, logic dictates we can also have a dependent event, where events do influence each other, do affect each other. Typically, one event will affect the other one. So an example would be, let's say a magician comes up to you with a whole deck of cards and says, pick a card, any card. You pick one out, and then he says, pick another one. Now, it doesn't seem like they influence each other, but they do a lot. Because if you've already picked out, let's say, the ace of spades, can you possibly pick out the ace of spades again? No. So your odds of picking a card out go from 1 out of 52 to 1 in 51. The odds were changed. They were influenced by that second one, by the first one. Okay. So, those are what independent and dependent events are. So let's get right into an example here. Example 1 is this: dependent or independent. Okay, so letter A. Let's see. Roll a 6-sided number cube and flick a color spinner. Okay, so my 2 events would be rolling a 6-sided number cube, the dice, and flicking a color spinner. Now, if I roll a 4, does that influence whatever color my spinner would be on? Again, no. So these would be independent. Okay. B, draw a random card out of a stack of 10. without replacing, draw again. Okay. So, say I have a stack of 10 cards. My probability of picking each of them would be, again, 1 in 10. Now, if I don't replace, if I don't put the card back, my second probability would be 1 out of 9. So, it is affected, so these would be dependent. I didn't realize that those are the examples. I just thought of stuff off the top of my head. They're very common sets of examples, so I apologize for the redundancy. Okay. Okay. Now, let's say I'm trying to find the probability of 2 outcomes on independent events. That's what we're going to focus on right now is independent events. So for the sake of just symbols, I want to find the probability of A and B, where A is one outcome and B is another outcome. So we get a little formula actually. If A and B independent, then, by gosh, an if-then statement, conditional, geometry 101, then the probability of A and B equals the probability of A times the probability of B. So, for example, if I were trying to find, let's say, the probability, I would get a heads if I flipped a coin, and I would roll a 3 on the dice. So I would find the probability of it. I'd roll a heads, which would be, or flip a heads, excuse me, which would be 1/2, or probability of A, which would be heads, so that'd be 1/2. And then I would multiply by the probability I'd roll 3, which would be the probability of B. In this case, rolling a 3, that's 1 out of 6. And then I would just multiply it, so I'd get 1 out of 12. Or, what is that, 8%? I think it's roughly somewhere around there. 1 divided by 12 times 100. 8.3%, my fault. 8.3 repeating percent. So that's how that would work. So, as always, let's do an example with it. Example 2, probability of independent events. So, what kind of situation we got here? Let's see. A desk has 5 red pens, 6 blue pens, 3 black pens, it has 24 silver paper clips, and then also has 16 white paper clips. What is the probability that we would get a blue pen and a white paper clip? Okay, so first we need to analyze and determine, are these independent events? If I were to rifle through this desk and pull out a pen, is that going to affect my paperclip odds? Vice versa, if I pull out a random paperclip, will that affect my pen odds? Well, no, unless of course, the pens get hooked to the paperclips are hooked to each other, all that stuff. So they are mutually exclusive, or they're independent of events. So I need to find the probability that I would get a blue pen. Well, the probability of blue would just be blue over the total. That's just probability old school, right? So I have 6 blue, but I have, let's see, 5 plus 6 would be 11, plus 3 gives me 14 total. And then 24 plus 16, I'm going to have 40 total paper clips. So my probability of blue would be 6 over 14. Then I also need to find the probability of white, which in this case would be my white paper clips over my total. So I have 16 white over 40. And then the last thing I need to do is just multiply. Okay. And multiplying fractions is pretty easy. We just multiply straight across. 6 times 16 is going to give me 96. And 14 times 40 is going to give me 560. However, 96 over 560 is not a probability, so we can just type that right in our calculator. 96 divided by 560. 96 divided by 560. That's going to give us 0.17 or 17%. And that will be our probability that we were to get a blue pen and a white paperclip. Just double check I got that. Okay. Now, we could also have events that are called mutually exclusive. Mutually exclusive events are events that cannot happen at the same time. Okay? That you just cannot do the events at the exact same time. A good example is if I rolled 1 dice, there is no possible way for me to roll a 1 and an even at the exact same time. It's just not going to happen. They would be mutually exclusive. I could roll a 1 or I could roll an even, and they'd be separate scenarios. Okay, they are events that just cannot happen at the same time. Now, the probability of mutually exclusive events would probability of mutually exclusive. Oh, that's not a very good one. Made it, right? So probability. Oh, this is not any good either. Okay, so if they are mutually exclusive, the probability of A and B is going to be 0. They just simply cannot happen at the same time. I made that one too. Now, the interesting thing is the probability of A or B would just be the probability of A plus the probability of B. So for example, if I were to roll a 1, that'd be a 1 out of 6. But if I wanted to roll an even, that would be 3 out of 6. So So the probability of A or B rolling your 1 or an even would be 4 out of 6, or 0.6 repeating. Okay. Now, let's go into an example with it. Example 3, mutually exclusive. So, students may, in a bigger school, students can only play one sport per season. No, Caden, you can't do track, cross country and football in this scenario. Students can only do one sport per season. Okay. 28% of them play basketball. And 24% are on the swim team. What is the probability that someone plays b-ball or swims? Okay. So, thankfully this problem breaks it down pretty easy for us. We would just need to find the idea of the probability of A, basketball. So looking for the probability of A, which would be probability of b-ball. And we also need to find the probability of B, which would be swim. And then we could just add them together, as we said earlier. Now, the good news is they're already broken down in percentages, so I get 28%, and I also get 24%, and I can just add them directly. That would be 52%. 28 plus 24, 52%. Okay, and this only works because they're exclusive. It says right there, students don't play one sport per season. There's no overlap. Okay. Now, things do get complicated when there is overlap, so let's talk about that. Next idea is called overlapping events. Okay. Overlapping events have common outcomes. Okay. So for example, if I'm going to take my dice, 6-sided number cube, wait, what's the example coming up? I don't want to use that. Let's say a deck of cards. What would be the probability that I would get a red card or an even number? Okay. Or. And let's just say it's just 1 through 10. Okay, no face cards. Well, from deck of cards, we know that there's 4 suits. If you didn't know that, there's 4 suits. There are hearts and diamonds, which are red. Then we have spades and clubs, which are black. Okay. So, out of all the possible red cards, there are 20 of the 40 would be red. Again, I'm just doing 1s through 10, so there's 10 of each suit. Now, of that, there are 20 that are even numbers. Okay. Now, if I were to add them, 20 plus 20, I would get 40 out of 40, which would be 100%. But there is possibilities that I could get a black card or an odd number, an odd black card, so it can't be 100%. So our formula has to change for overlapping events, and it actually does. The formula turns into P of A or B equals P of A plus P of B minus P of A and B. So we still get our 20 plus 20, which is fine. However, we have to subtract this P of A and B. What this turns into is the overlaps. Now, if I were to go through and count it, I'd have 2, 4, 6, 8, 10, and 2, 4, 6, 8, 10 of the hearts and diamonds. Again, those cards that are red and blue. And there I would have, again, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. I'd have 10 total cards. So I'd have to subtract my 10 out of my 40. So I would get 20 over 40 plus 20 over 40, which would be 40 over 40, minus 10 over 40, which would give me 30 over 40 in the situation, or 75%. What happens is, if we were to just do straight adding, some of those cards would be counted twice. Some of the even red cards would be counted twice because they apply to both situations. That's why we have to subtract when they get doubled up. So on overlapping events, it's P of A plus P of B minus P of A and B. You're subtracting that extra scenario. Okay. And then we're going to do an example, and then that'll be it for 13-4. Example 4, overlap. So let's see, what is the probability of rolling an even number or a multiple of 3? And we're just going to do one 6-sided cube. Okay. One 6-sided cube. So my A event, P of A, which would be my probability of rolling an even number. Well, if I have a 6-sided cube, I could roll a 2, 4, or 6. So my probability of rolling an even number would be 3 out of 6. Okay, nothing crazy about that one. My probability of B would be my probability of a multiple of 3. Multiple of 3 just being 3, 6, 9, 12, etc. Now the only ones on that set number cube would be 3 and 6. So the probability of a multiple of 3 would be 2 out of 6. Now the last thing again we need to consider is the probability of A and B. Is there any outcome that exists in both those lists? And if so, how many? Well, yes, the outcome that exists in both those lists is at 6. So the probability of A and B would be the probability of 6, which would be 1 out of 6. So now I just need to do my formula. Probability of A plus the probability of B minus the probability of A and B. So I get 3 out of 6 plus 2 out of 6 minus 1 out of 6. 3 plus 2 is 5, minus 1 is 4. So 4 out of 6, or 66.7%. And I know it's 0.6 repeating. I'm just going to go with 0.7 is fine. Okay. But hopefully that example, with some things that are easier to visualize, show why we have to subtract the overlap. Because otherwise, we would count this 6 twice. That's why we subtract the overlap, just one of them. Okay. Now moving on to 13-5. Probability models. So the first thing we need to talk about is what's called a two-way frequency. A two-way frequency, all it is just a frequency table with two categories or sets of data. Okay. So an example would be, let's say, dogs and cats who had fleas and did not fleas, no fleas. Let's say we had 7 dogs with fleas, 3 with no fleas. We had 0 cats with fleas, or I'm sorry, we had 2 cats with fleas, and then we had 8 without fleas. Okay, so this would be a normal set of data. And now the only difference is, instead of having one static total, we have 4 different categories to break down these totals in. We have total of dogs, which in this case 7 plus 3, so 10. We have total of cats, 2 plus 8 is 10. And then we also have total fleas, 7 plus 2 is 9. And no fleas, 3 plus 8 means 11. With two-way frequency, we have 4 different total categories. Okay. Example 1. Two-way table. Let's say that we have males and females. We're just going to go with those two. I'm sorry, just how the book does it. And then we have that; those are in activities, and those non-activities, not activities. Okay. I don't want to say sports because we always know that there are more activities than just sports. Obviously, you could be in quiz bowl, band, vocal, play, etc. Okay. Let's say we have 112 males in sports, or I'm sorry, in activities. And then we have 145 not in activities. Females, we have 139 in activities. We have 120 not in activities. Okay. So again, we need to determine our totals. Total males we have would be 112 plus 145, which is 257. Total females, 139 plus 120, so 259. Total activities, we get 251. Total non-activities, we get 265. Oh, and then typically you'll see one more little category down here, one more little box. What do you think that is? The overall total. And the crazy thing is, these numbers should match up, and we actually get 516 total. So let's see. 257 plus 259 is 516. 251 plus 265 is 516. So Just 516 is the total. Total of everybody involved. Okay? So, we need a question. Find the probability that if we were to pick someone at random, we would pick a female not in activities. So, these two-way frequencies are kind of interesting. It works exactly like you think it should. Okay. So first we need to think of, well, how many females are not in activities? Well, we can find females in this here and not activities here. Obviously there are 120 not in activities. Okay. So we get females, no activities. And whenever we're finding probability, we take that over the total. So in this case, we have to use the total, not just the female total, because we don't know for sure that we're going to pick a female if we were to randomly choose a student. So I get 120 divided by 516. So if I were to randomly choose a student and the probability to be a female who's not in activities would be 23.2%. Now this helps set up the idea of what is called a conditional probability. So I'm going to erase this. A conditional probability. A conditional probability is this idea of if A, then B. So the way we do that is also listed as P, B, bar, A. What this means is that A is a prerequisite for B. We know that A happened. A has to happen. We need to find the probability if B happens if A is already for sure. So the way we do that is we find the probability of A and B, and then we divide it by the probability of B as the total, because B is often the less restrictive of the two. So we find the probability that both happen over the probability of the total of B. Again, typically B is the less restrictive. Let's see. So, another chart. So let's see. Example 2, fun probability. Example 2, conditional. Okay. 1,000 people were surveyed. About an upcoming bill. The legislature organized their thoughts and age groups. Find the probability that they had no opinion if they were over 60. Okay. In the book, it's this legislature was increasing the minimum wage. So let's see, categories. We need ages 18 through 29. Oh shoot, I'm gonna go down a little bit. 18 to 29. We also have 30 through 45. We have 45 through 60, and then we have 60 plus. We also have people who are for increasing the wage gap. Increasing minimum wage. We have people against increasing minimum wage, and then we have people who had no opinion. Let's see, numbers. We had 310 younger people for increasing minimum wage. We had 50 against, and we had 20 with no opinion. So our total we get is 308. Second group, we had 200 that were for increasing it. We had 30 against, and we had 10 with no opinion. So we end up with 240 total for that age group. 45 through 60, 120 said, hey, raise the wage, raise minimum wage. We had 20 who said, no thank you, I don't want that money. And then we had 30 who were like, it's fine. So that gives us 170 total. And then over 60, we had 150 who were for it. We had 20 against, and we had 40 with no opinion. So we had 210 total there, and we have 1,000 total. Now, if we were to take the total of our for category, we get 780 people were for the category. We had 120 who were against, and then we had 100 people with no opinion. Okay. So our question says the probability that they have no opinion if they're over 60. So I first need to find the overlap, so I need to find the 60 and the no opinion. In this case, our overlap would be 40. And then I need to put it over the first condition. The condition already is for sure happening, be 60. And how many total 60-year-olds do I have? In that case, 210. So I get 40 over 210. Let me just make sure I did that right. RIP. It appears that I flipped that. That's not fun. I flipped it. The second one has to happen. My fault. So I get 40 over the total of the no opinion, which would be 100. So I get 40 over 100, which would be 40%. So the second one is the one that has to happen. Second has to happen. I'm glad I went and double checked that. So if they have no opinion, what's the probability that they are 60 years old? That's how we should read that. So I look at my no opinion category, and if I were to pick one of those people at random, what's the probability that it would be over 60? So 40 over 100. Okay. Now, sometimes, instead of having raw numbers and totals, you'll just be getting decimal values. So, those relative frequencies. So, let's do that. Example 3, relative frequencies. Remember back in last week we were where you would just find the percentage or the decimal value of each category? Well, the same thing can be applied to these tables. So here, a company, I hold this in, a company, some sales company, a sales company has a seminar. Probably someone like Dwight Schrute or something just to talk about how to move their product, maybe paper, who knows. So the sales company has a seminar. The vice president, after 2 months, documents who went, who didn't go, who went, who didn't, who sold more, and who didn't. So we have 2 sets of data: who went to the seminars and who increased their sales. So we can again plot that. So let's see. People who attended the seminar, people who did not attend, we have some people who increased their sales and some people who did not increase. Now, it doesn't necessarily mean they decreased, they could have just kept it static. So, the people who increased their sales and attended, that was 0.48. So 48% of the company attended and then increased their sales, which is great. Okay. Now, 0.02 did not attend, but they still increased their sales anyway. And overall, that's half the company increased their sales. So we have 0.48 plus 0.02, so 0.5, which would be 50%. That's pretty good. Now, okay, 0.32 attended but did not increase their sales, which isn't very good, which kind of stinks. They went there and they didn't get better. Now, 0.18 didn't attend and they did increase their sales. So then I get 0.32 plus 0.18 gives me 0.5. 0.48 plus 0.32 gives me a total of 0.8. And 0.02 plus 0.18 gives me 0.2. And 0.5 plus 0.5 is 1. 0.8 plus 0.2 is again 1, which makes sense because obviously someone has to fall into one of those 4 categories. 2 of those, yeah. Now, we define the probability that attended and increased sales. So let's see which one's technically first in the book. Okay. Okay. So it says if attend, then increase. That's what we're trying to find here. So my attend would be A, and my increase would be B. So first we need to find the probability that they attended and increased. So attended and increased there. Probability of A and B over the probability of A. Gotcha, there's where I messed up because on the slide I said probability of B on the bottom, didn't I? Found it. Sorry. Okay, so probability of both would be 0.48. Now, what's the probability that they attended? Attended would be 0.8. So I can just still use that raw data just like normal numbers. 0.48 divided by 0.8. And I'm going to get 0.6 or 60%. So if they attended, they had a 60% chance of increasing there sits. That was a lot, I know it was, but that's all I got in both those sections. Thank you for listening and taking notes. And I was told to plug it, as in saying is, please be sure to like, comment, and subscribe, but I think that's cringy. Have a good day.